Let's do section 1.6, inverse functions and logarithms, and let's wrap up chapter 1, this preliminary stuff. So we're reviewing more material from Pre-Calculus 1, inverse functions and logarithms. In the PDF posted online, you'll find links to some Pre-Calculus 1 notes, pretty thorough notes on this same type of material. What we're about to do here is a quick review of that, really. So when talking inverse functions, the first topic you always encounter is the concept of one-to-oneness. A function, f, is one-to-one on domain D if f of x1 not equal to f of x2 occurs whenever x1 is not equal to x2 in domain D. In other words, you put different things in, you get different stuff out. We can express it geometrically as a horizontal line test. How about that? So that's the easiest way to give an intuitive feel for what the logic there implies. A function, y equals f of x, is one-to-one if and only if its graph intersects each horizontal line at most once. So vertical line test was we have the graph of a function if vertical lines intersect the graph at most once. Here we're talking about the fact that we're given a function, but this additional property of one-to-oneness. So for example, illustration from the book, y equals x cubed is a one-to-one function. We've seen graphs of powers of x, power functions. And this one's one-to-one. I draw an arbitrary, in red, horizontal line. Wherever we place that, it's only going to intersect the graph of that function in one point. If we look at the square root function, draw a horizontal line. Wherever we draw it, it's going to intersect the blue graph of that function in at most one point. So exactly one point, if I draw that horizontal line at or above the x-axis, I draw it below the x-axis, it doesn't intersect the graph of that blue function at all. So that's why the at most once. Some examples of non-one-to-one functions. Squaring function, y equals x squared. Draw a horizontal line. At 0, a horizontal line passing through the origin intersects it in only one point. Lines below that don't intersect it at all. The problem is lines above that will always intersect it in 2 points. So here we put in two different input values, -1 and 1, yet we get the same output value. So in terms of input and output values, x1s and x2s as described in terms of the definition, this violates that because we put in two different values, x1 and x2, yet we get out the same output value of 1. Both 1 squared and -1 squared are each 1. It's not a one-to-one function. Sine functions aren't one-to-one. In fact, none of the 6 trig functions are one-to-one functions. Take a sine function, for example. If we'll look at a horizontal line, it's going to intersect that curve in more than one point. I draw the whole sine function, it's going to, a horizontal line that intersects it at all will intersect it in infinitely many points. Here, I only need more than one to show that we don't have one-to-oneness, so we can draw a segment of the sine function. Draw the line y equals 1/2. We get intersections at pi 6 and 5 pi 6 for a sine function. Sine of both of those angles is 1/2. So not a one-to-one function. Okay, we only look at one-to-one functions in an algebra class because we're interested in inverse functions. So we'll be able to find inverses of one-to-one functions. Unfortunately, we're going to want to try to find some inverses related to some non-one-to-one functions. Let's look at the first example from this section where they give us a piecewise defined function, and they say determine from its graph if this function is one-to-one. Okay. It's defined, well, I guess first, it's defined piecewise as 2 minus x squared for x less than or equal to 1 and x squared for x greater than 1. So we need to rely on what we know how to graph, and you're supposed to know how to graph y equals x squared, maybe how to graph parabolas in general, quadratic functions in general. But here we'll look at this in the spirit really of our textbooks, section 1.2, maybe in terms of some reflections and translations. The pieces of this function all involve the x squared function. The second piece actually just is the x squared function, and you know how to graph that. The first piece is 2 minus x squared. So let's create 2 minus x squared by starting with this function x squared and then doing some elementary things to it. First, let's take the x squared function and multiply it by a negative. Okay, you know the x squared function is an opening upward parabola with its vertex at the origin. I put a negative sign on there. It reflects that to its mirror image about the x-axis. It replaces every y value with its negative when we multiply through multiply y values by a negative is effectively what we've done. So y equals negative x squared is an opening downward parabola with its vertex at the origin, and we can plot a handful more points if you like. Plotting points is a bad way to graph, unless there's special points and you know why they're special, or there's special points and you already know the shape of the graph, and you know the shape of an x squared graph. It's a parabola. A quadratic function has a graph that's a parabola. So I'll plot the vertex and a handful of other points, and not just plotting points, but plotting points and using other information. That is a good way to graph. But just willy-nilly plugging in points and plotting them and connecting them, bad way to graph. Knowing what you're doing and strategically plotting points, that's a good way to graph. And we know this is a parabola. So we get this for the y equals negative x squared. We want that to have 2 added to it. So we got, if you like, negative x squared plus 2. So that just moves all those points up 2 units. It moves the whole parabola up 2 units. And y equals 2 minus x squared looks like this. So very much explained in the spirit of section 1.2. When we looked at reflections, this is a reflection about the x-axis of y equals x squared, reflect it, produce this, and then a translation upwards of 2 units to produce that. All right, so let's see, that's a piece of the f of x function. The other piece, well, you know how to determine that. So what we'll do is graph this piece over the appropriate x values, x less than or equal to 1, and the other piece for x greater than 1, glue them together and see what we get. Here's what we get. So for x less than or equal to 1, we'll take that opening downward parabola, all right, up to here. Now we'll graph y equals x squared and only keep the part for x strictly greater than 1. So the parabola would be something of this sort, right? It would be an opening upward parabola. In fact, it would pass through the point 1, 1 and the point negative 1, 1. Strictly speaking, the blue point here comes from the opening downward parabola and not the opening upward ones because of the piecewise way that the function was defined. Anyhow, it looks like we get a continuous piecewise defined function. So here's the graph of the piecewise defined function. Question was, is this one-to-one? So the question may as well be, does this satisfy the horizontal line test? I take horizontal line on down here, no problem. Intersects the curve exactly once, exactly once, exactly once, exactly once. Oops. When I reach the horizontal line y equals 1, it intersects the curve in 2 points. Sufficient to say that function's not one-to-one. All right. So we see from the graph that it's not one-to-one. I can explain it a handful of ways. The value 1 is attained, say, for 2 input values, x equals 1 and x equals negative 1. The value 2 is attained for 2 input values, 0 and square root of 2 over here will also produce a 2 out. Actually, anything between 1 and 2, I draw a horizontal line, y equals a constant, where that constant is strictly greater than 1 and strictly less than 2. So anything between, strictly between 1 and 2, it's going to intersect it in 1, 2, 3 places. You told me the constant, I can figure out the places. But certainly horizontal lines will intersect this in more than 1 point. 2 points at y equals 1, 2 points at y equals 2, and 3 points for y equals a constant, where that constant is between 1 and 2. So yeah, it's got problems with the horizontal line test. That's why it's not 1-to-1. So back to the notes. And as mentioned earlier, we would look at one-to-oneness because we're interested in inverse functions. Suppose that f is a one-to-one function on a domain D with range R. All right, well, see, thing is, we're going to be interested in inverse functions for functions that aren't one-to-one. So we'll have to fix them in a sense, because the following definition of inverse functions only valid for one-to-one functions. The inverse function f inverse is defined by f inverse of b equals a if f of a equals b. We've really just interchanged the roles of a and b. Over here, a is inside the function and b is the function value. Over here, b is inside a different function and a is that different function's value. The claim is the domain of f inverse is R, the range of function f, and the range of f inverse is the domain D of the original function. So domain and ranges have been interchanged. Domain is R, range is D. Oh, that sounds backwards. Well, it is backwards because you've interchanged the roles of the input and the outputs effectively. And because of that, if we were to graph a function and its inverse on the same collection of axes, then we can produce the graph of an inverse function by interchanging x and y values. That's what the definition implies. What that implies in terms of graphs of functions and their inverses is a mirror image relationship. That is, the graphs of f and f inverse will be mirror images of each other with respect to the line y equals x. So we've got, which is which? We've got a blue function, f of x. So f of x is function f. And the rumor has it this yellow function is its inverse function. All right. So if you would imagine taking the blue function, drawing this on a piece of paper, folding it over about the line y equals x, 45-degree line through the origin, sorry, pi force radians, angle line through the origin, the line y equals x. Then what would happen is, if we were to fold this over about this dotted line, this positive x-axis would fold over and lie on top of the positive, they've interchanged the letters here. This axis would fold over and lie on top of that axis. That axis would fold over and lie on top of this axis. The positive y-axis and positive x-axis would be interchanged. The negative x-axis and the negative y-axis would be interchanged. That's the reason this one looks weird. They've labeled the horizontal axis with a y and the vertical axis with an x. Well, they've already done that interchanging, is what it amounts to. But the graph of the function then would fold over and lie on top of the graph of the inverse function. If we were to draw a horizontal line, say draw a horizontal line through this point AB, what would happen to that line if you interchange the x's and the y's, if you folded it about this line y equals x? Think about it, but try to visualize the following. A horizontal line drawn through this point AB would fold over and become a vertical line passing through this point BA. Take a mirror image of it about the line y equals x, and what you would get then, a reflection, if you like, about that line, would be a vertical line through this point BA. If I were to take this vertical line and fold it about the line y equals x, it would produce the corresponding horizontal line. So this interchanging of x's and y's interchanges horizontal lines for vertical lines. Now, if I got a graph of a function, it has to satisfy the vertical line test. So when I fold it over, all them vertical lines are going to become horizontal lines. So the only way we can have a function that has an inverse function, where that inverse function would have to satisfy the vertical line test, is to have a function itself which satisfies a horizontal line test. Well, that's the reason one-to-oneness is important. So we only have functions with inverses when we have one-to-one functions. What that means in terms of pictures is, if I've got a function that satisfies a horizontal line test, then I can fold it about the line y equals x and find an inverse function. And this inverse thing, it will be a function, that is, it'll satisfy the vertical line test, because all of the horizontal lines of interest for function f have folded over to become vertical lines when we do this interchanging of x and y. So that's the reason you have a one-to-one test, so that we can have an inverse function. That is, have an inverse that satisfies a vertical line test. So it's ultimately all about vertical line tests, but there's this interchanging of x and y when we look at inverse functions that makes horizontal lines become a thing of interest. The process of passing from f to f inverse can be summarized as follows. This is finding the inverse function algebraically, assuming we start with a one-to-one function. Solve the equation y equals f of x for x. So you'll be given an equation that represents the function, write it as y, as some equation involving x, and solve for x. I got a little bit of bad news for you. And solving for x can be a monstrously complicated problem, even when the equations aren't too involved. We got something harder than maybe squaring. We got something more complicated than a quadratic function. This could be exceedingly difficult. Of course, the good news is they don't ask you the exceedingly difficult ones. But, I mean, the manipulations are easy to describe, maybe not so easy to perform though. So we'll stick with easy functions and easy things that we can actually do these manipulations for. And it ain't just you because you're just taking a freshman math class. Nobody can solve these complicated equations. There's a level of insolvability involved. So the reason you deal with what you deal with is because, well, it's the kind of thing you can do. It's the kind of thing that most folks with the knowledge can do. The other stuff, nobody may be able to do. It may be undoable. Take a graduate or senior level modern algebra class and you get into the algebra of this. For our purposes, as complicated as we'll get is probably quadratic functions, maybe some cubing functions that are pretty simple. But solve for x in terms of y. That's what we'll do. And then the formula x equals f inverse of y is what we'll produce. We'll then interchange, step 2, interchange x and y. You knew that was coming from the previous discussion about interchanging and folding over Cartesian planes about the line y equals x. Interchange x and y, and then you'll get the formula y equals f inverse of x. So solve for x, interchange x and y, and then you get y equals the inverse function of x. Let's do that. Let's do it for the squaring function. Okay, so we'll go to the supplements and look at this. Let's talk about it a little bit first though. So you're about to find the inverse of the squaring function, sort of. If we look at y equals x squared, and we were just doing that not long ago, you get a parabola. But parabola, that's not one-to-one. We had a picture of that not long ago. Parabola will violate the horizontal line test, and it's not a one-to-one function, and it ain't got an inverse. The squaring function per se, the squaring function by itself, doesn't have an inverse function because it's not a one-to-one function. So we can't consider, cover this part up for a second, we can't consider just y equals x squared. It's not a one-to-one function. It doesn't have an inverse. So what we're going to do is restrict the domain. So we're going to consider the function y equals x squared with the added condition x is greater than or equal to 0. What that is we'll graph y equals x squared and then erase the left-hand part of it and just keep the right-hand part. That's what this is. So if we graph y equals x squared with the added condition that x is greater than or equal to 0, we get the right-hand half of a parabola. That satisfies the horizontal line test, and that is a one-to-one function. So y equals x squared by itself, not one-to-one, doesn't have an inverse. Y equals x squared with a constraint, x is greater than or equal to 0, that does have an inverse because it's a one-to-one function. And example 1.6.4 is to find that inverse. Of course, it's a square root function. Okay, so let's go through that and illustrate that two-step method while we're in the neighborhood. Okay, so we'll write y equals x squared. Remember, x is greater than or equal to 0. That's part of the definition of the function. We'll use it in the next line or two. Solve for x in terms of y. So we'll take a square root of both sides, square root of y, square root of x squared. What's the square root of x squared? Absolute value of x. Don't forget the absolute value. That's actually how the absolute value can be defined. It's done in, I think it's Appendix A1. They deal with some absolute values. I think that's where it is. Either that or somewhere in Chapter 1. Don't forget, when you take the square root of something squared, you don't just get the x, you get the absolute value of x. So we're looking at a situation where the square root of x equals the absolute value of x. But wait, that's not all. X is greater than or equal to 0. That was part of the definition of the function. Since x is greater than or equal to 0, then the absolute value of x and x are the same thing. So we can drop the absolute values because we know x is non-negative. If x was negative, we couldn't do this and some other stuff would happen. So with all the information we're given, we get the relationship square root of y equals x itself. Step 1, we solve for x in terms of y. There it is. Step 2, interchange x and y. So then we get the square root of x equals y. Square root of x equals y, or y equals the square root of x. And that y equals the square root of x, that is rumored to be the inverse function. Yeah, of course, for a squaring function appropriately modified, I'm going to have something involving square roots for the inverse function. Well, we're in the neighborhood. What if we took the graph of y equals x squared where x is less than or equal to 0? So over here, instead of taking the right-hand half of the parabola y equals x squared, what if we took the left-hand half of it? What do you think could happen then? Then we'd have the condition x is non-positive. Well, we couldn't do this anymore. We couldn't replace absolute value of x with x itself. If we knew x were negative, non-positive, we'd have to insert a negative sign there. And when all the dust settled, you'd end up with the inverse function in that case as a negative square root of x. We've dealt with this before about the square roots always being non-negative. Though you may be working a problem where you're interested in the negative square root. What's the square root of 9? 3. That's what the square root of 9 means, is the positive square root of 9. Yeah, well, it's true that negative 3 squared equals 9 as well. Well, if you wanted the negative square root, then you'd have had to ask for it. Were we to modify this original function to a different function that involves x non-positive, then that non-positivity, all that negativeness in a sense, would cascade down and we'd end up with a negative square root down here. We can only talk about inverse functions when we deal with one-to-one functions. The straight up f of x equals x squared function doesn't have an inverse because it's not a one-to-one function. You take the right-hand half of it, it's got an inverse function. That's what we just did. If you take the left-hand half of it, that's also one-to-one and has an inverse. Turns out it's the negative square root of x function. Back to the notes. Let's do another one, I guess. Number 22. Okay. Here they give a graph of f of x equals x squared minus 2x plus 1, where they've made the constraint x is greater than or equal to 1, and its inverse. They want us to find a formula for the inverse. Okay, x squared minus 2x plus 1, where x is greater than or equal to 1. Quadratic function. I'd expect its graph to be a parabola. A part of a parabola because they've done something over here with the x greater than or equal to 1. I'm going to trust them that the graph of x squared minus 2x plus 1 would be a parabola with its vertex at 1, be something like this. So when we add the additional constraint that x is greater than or equal to 1, we lose this left-hand half and we keep this part. Why'd they put that in? To give you a one-to-one function. Without a one-to-one function, there is no inverse. And they claim this is the inverse function. Does the picture look right? What should be the relationship between the blue function and the yellow inverse function? If I were to draw a line y equals x, I should be able to fold the yellow curve onto the blue curve and vice versa. Y equals x, yeah, that point right there would be fixed. It lies on both of them. What would happen is this yellow part here would fold over to lie on top of the blue part here, or vice versa. And say the blue part up here folds over to lie on top of the yellow part there, or vice versa. Yeah, the graph looks reasonable, that these are reflections about the line y equals x of each other. All right, so they want a formula for f inverse. Fine, they gave us a formula for f of x. All we got to do is this two-step procedure. We'll let y equals x squared minus 2x plus 1, where x is greater than or equal to 1. Maybe not the ideal place for a new line, but this is part of the formula, that x is greater than or equal to 1. All right, how about I rewrite this as, let's take the y to the other side and rewrite it as x squared minus 2x plus 1 minus y equals 0. Take the y to the other side, and we've got a quadratic in x. We've got an a b, and a c. Ax squared plus bx plus c equals 0. Except the c involves a y value as well. Yeah, so what? I can still use a quadratic equation. So let's treat this as a quadratic. It is a quadratic. And let's solve for x. We still got this information about x greater than or equal to 1 floating around in the background. All right, solve for x. Using the quadratic equation, we'll get x equals negative b. B is negative 2, plus or minus the square root of b squared. B is still negative 2, minus 4a. A is the coefficient of x squared, it's 1, times c. C is a constant term. It's 1 minus y. All right, all over 2a, a is still 1. Okay, so let's see, negative 10 give us a positive 2, plus or minus. Here we'll get 4. Distributing here, we'll have minus 4 plus 4y. That was 4 minus 4, gone. Plus 4y, we're left with a square root of 4y. In the denominator, we just got a 2. Square root of 4 is 2, so let's bring that out front, and let's simplify it a little bit. So we get 2 plus or minus 2 on the square root of y over 2. Divide that 2 into each of those, giving us 1 plus or minus the square root of y. We've got x equals 1 plus or minus the square root of y. And over here or up here, remember, we've got the condition as well that x is greater than or equal to 1. The square root of y, all by itself, just the square root of y part, that's non-negative. So you're going to add something non-negative to 1 or subtract something non-negative from 1. Well, if x is greater than or equal to 1 and x equals 1 plus or minus some stuff, you better be adding some stuff, adding some non-negative stuff. So that's how we'll get rid of the plus or minus on the next page. Okay, so here's where we left off. We had x is 1 plus or minus the square root of y. But remember, x is greater than or equal to 1. So which you going to choose, the positive or the negative? Oh, must be the positive. If I subtract square root of y, remember square roots are non-negative, we'd be making something potentially smaller than 1. And we've got x greater than or equal to 1. So choose the positive on the square root. Where'd that plus or minus come from? Quadratic equation gave it to us. Totally valid in the absence of other information to say x equals 1 plus or minus the square root of y. But we did have extra information. X is also greater than or equal to 1. Then x must be 1 plus the square root of y. Step 1, we solve for x in terms of y using all the information. Interchange x and y, giving us y equals 1 plus the square root of x. And so that must be the inverse function. Y equals f inverse of x must be 1 plus the square root of x. You may not be totally awesome at graphing. You will be when I get done with you. So when we get through this calculus 1 stuff, you'll be just as good as anybody else at graphing things. But I think you probably know how to graph a square root function. It's half of a parabola. I think we saw a graph earlier. So we got half of a parabola shifted up by 1 unit. That's what the yellow thing is. So that seems to be pretty consistent with a picture also of what we have. So there's the inverse of this function. What if they had have given us that original function with x less than or equal to 1? Well, then we would have taken the negative, and the inverse of that would have been 1 minus the square root of x. What we would have had then in blue would be the missing left-hand half of this function instead of the right-hand half. And what we would have gotten here is the missing bottom half of that parabola instead of the given top half. So flipping these inequalities has a very geometric meaning with these quadratic functions. Back to the notes. Let's talk about log functions. The logarithm function with base a, y equals log base a of x is how that is read. I'm sure you've encountered these before. It's the inverse of the base a exponential function, y equals a to the x, requiring a to be greater than 0 and not 1. Requiring a to be greater than 0 because, geez, that exponential will have some problems with square roots and negatives if I allow a to be negative. If I allow a to be 0, then we're getting a constant function out. If I let a equal 1, we're getting a constant function out on this exponential. It's not 1-to-1. So the logarithm wouldn't exist in those cases. So that's the reason we're making this constraint on the base, that it be positive and not 1. Inverses of exponentials. Well, you know how to graph exponentials. So you ought to know how to graph log functions. The domain of a log function is, shrink this so we can see the picture and the conversation at the same time. The domain of log base a of x is 0 to infinity. It should be the range of a to the x. For example, here's y equals 2 to the x. What's the range for this function? The range is the stuff that comes out. It's everything greater than 0. That's what we get out of the y equals 2 to the x function. All right, that would be the domain of the inverse function, the domain of the log function. Here, rumor has it as a graph of the log function. What's its domain? Looks like it's got a vertical asymptote at 0. That ain't in the domain. It's not even defined over here either. Negatives aren't in the domain. Everything greater than 0 is in the domain of the yellow log function. Oh, and if I take the blue function and fold it along the line y equals x, it'll lie on top of the yellow function. The usual thing, the interchanging of x's and y's. So domain of log base a of x is 0 to infinity. The range would be the domain of the 2 to the x function. Look at where the blue function is defined. It's defined everywhere. They don't graph it over here too far to the right because it grows too fast. All right, then that means the output of the log function will be all real numbers. They didn't graph it for very big y values because that would require us to go extremely far to the right to get those points. Just as the blue function grows extremely quickly, the yellow function grows agonizingly slowly. It's because of that mirror image relationship, in fact, about the line y equals x. It's natural for us to consider logs base e. I guess I should back up. The book does mention common logs, logs base 10. When a equals 10, log base 10 of x is called a common log function. Sometimes that's denoted log of x. Sometimes log of x means something else. So be careful on the context of the book you're using. If you take a psychology class and they talk about decibels, we've mentioned decibels in the past, it's a log scale. It's a log base 10 scale. Other log base 10 scales. I think pH is a log base 10 scale. Richter scales are log base 10 scales. So log base 10 is commonly used. Yeah, well, it ain't used in math and science-y classes where you'd be using calculus. If you're using calculus, you're going to use logs base e, and those are called natural logs. So when a equals e, the base of the natural exponential function we discovered in the last section, then log base a of x, that is log base e of x, is called a natural log function. in physics classes and engineering classes and math classes, when you discuss logs, they're very likely they're natural log functions. In some books, log of x will denote natural log. You talk log, you talk logarithms in a physics class, it's probably natural logarithms. You talk logarithms in a future math class, it's probably natural logarithms. I love Thomas's Calculus, the book we're using, but they're not going to use log of x, not our text, when they're talking about natural logarithms. They're going to use ln of x. Here it is down here in the picture. So they'll denote those natural log functions as ln, logarithm natural, I guess. But beware, when you see log of x without a base written, depends on where you are. If you're in a math or science class, it's probably natural logs. It's probably base E. Elsewhere, I don't know, geology classes, agreed, those are science classes as well as is psychology. But check it out. It's unclear when they leave the base off, whether they mean base 10 or base E. If they write LN, they mean base E. In your future math classes, when you see log like this, it probably means natural log, though. Check what the book has to say about it, but it's super common after the freshman level to use log to indicate natural log. Of course, you're using natural logs. You'd be nuts to use logs to any other base for reasons I can't quite explain yet. There's big advantages to using natural logs. Some algebraic properties of natural logs, and as we'll see of all log functions, is if we take any positive numbers, b and x, they didn't use a and b, they used b and x. They've got their reasons. These properties will be established somewhere deeper in the book. These are not new things to you, though. You're used to seeing this kind of behavior for log functions. The log of b times x is the log of b times the log of x. So the log of the product is the sum of the logarithms. The log of b divided by x is the log of b minus the log of x. The log of the quotient is the difference of the logs. The log of 1 over x is negative log x. You know, all three of those remind me of the behavior of exponents. When you're multiplying, add exponents. When you're dividing, subtract exponents. A negative exponent means take a reciprocal. You know why those are behaving like exponents? Because logarithms really are exponents. Remember, we can relate any log equation to an exponential equation. Log functions are inverses of exponential functions. So the fact that these remind me, these first three at least, remind me of behaviors of exponents, that ain't a coincidence. And the final power rule is the natural log of x to the r power is r times the natural log of x, so that r exponent comes out front when inside a natural log function or any log function, it turns out. So let's use